Hi, I'm Natalia from the University of Glasgow, and today I will talk about the work that we do in the release project, which is a European project, and we have 8 partners. So we have 5 academic partners from UK, then Greece and Sweden, and we have 3 industrial partners. These are EDF, Erlang Solutions, and Ericsson. In particular, I will talk about the work that we do at Glasgow University, Heriot-Watt University, and Ket universities. So, and that is about scaling distributed Erlang. Oops. I'm sorry. It doesn't listen to me, right? Right. Something happened with the slides. For some reason, they went just switched forward. Sorry, yeah, that's okay. Backward. Right. So I'll briefly introduce the release project for those who haven't heard about it. And I will talk about the limitations of distributed Erlang and why we want to scale it, and then about scalable distributed Erlang. So it will be about what we do, how we do, and why we do those things. And I will not go into too much details, rather will give you a flavor what's happening and why we do that. So first of all, the release project. The release project is about scaling the radical actor model. And that is about building reliable software on the massively parallel machines. And here we talk about something like 10 to 5 cores. For that, we use Erlang, and we use on 3 levels. So we work on the VM level, on the language level, and with tools. And I will talk about the language aspects. So, and this is the typical hardware that we kept in mind when we were thinking how would we scale Erlang. So first of all, that is commodity hardware with the non-uniform communication. And then we thought about something like, so we have clouds, and we have servers, something like 3-5 servers per cloud. And then each server would have something like 100 hosts, and those hosts would contain those modules. And each module would be an SMP module with 6-8 cores. So distributed Erlang. Well, first of all, this famous picture. So we have hosts. These are blue. Oh, I'm sorry. Yeah, we have hosts, and a host can have multiple number of nodes, and then they have multiple cores, and we have processes inside. But the thing is that we have a fully connected network. Of course, we can switch that off, and we can have hidden nodes. But here we talk about normal nodes with a fully connected network. And another thing about distributed Erlang is that we have these explicit placements. So when we want to spawn a process on another node, we need to explicitly say which node we want to spawn it to. And that's fine. Of course, distributed Erlang is also about reliability. And this is React benchmark. So what we do, we have nodes, and then we just killed some of those nodes and the system in a stable state. Then we get those nodes back and the system in a stable state again. So React, this is a DBMS, distributed database system, and they use Erlang, and they use this reliability model. So what's the problem? What's the limitation Erlang scales? Well, the problems are, for example, with this global namespace. So, for example, if we use global module, then as soon as we start registering names there, then we get into problems. And here, this picture, it shows a DE bench, which is a modification of Basho bench. And we have a fully connected network, and we have this tiny rate of global operations. And then we can see how the performance, so here we have throughput, number of nodes from 10 to 100, and then we can see how with even 0.005% of global operations, the performance start degrading. And of course, global operations, they're not only about global module. They're about, for example, using RPC calls on multiple nodes. And these are also global operations. Another problem is with single process bottlenecks. So we run an experiment with React, and then we have again throughput, we have 10 to 100 nodes, and then we can see that it scales beautifully up to 60 nodes, and then there is some stop at 70 nodes, and then the performance goes down. And by the way, this is React version 1.1. They did some modifications that, unfortunately, we didn't measure that anymore. But the thing here that there was a huge problem with single process bottleneck there. And we think also due to all-to-all connections. So our design approach. Well, when we need to scale a system, we need to scale, first of all, persistent storage, and we need to scale in-memory data structures, and then we need to scale the actual computation. So, well, we thought, well, the React and Cassandra, they're quite good with scaling those things, so we leave that to them. And then in-memory data structures, and here we talk about edge tables, and this work is tackled within the release project, and Uppsala and Ericsson work on that. So our bit is about computation. And here we had those design principles, how we want to approach that. And that is about working on the Erlang level as far as possible. Then we want to preserve the Erlang philosophy and programming idioms. So Erlang philosophy, it's about let it crash and then share nothing. And then we want to keep the Erlang reliability model unchanged as far as possible. So these are three main design principles that we kept in mind when thinking about scaling distributed Erlang. So what is SD Erlang? Well, SD Erlang is a small extension of distributed Erlang, modest one. And here we looked at two parts. So the first one is about network scalability. So we have this problem that we have a fully connected network, and what we want is to reduce that. And this reducing all-to-all connection and reducing the shared namespace. And we tackle that by introducing as groups, by grouping nodes. And then another problem is semi-explicit placement. So the problem here is that it's fine if you have a small system and you know every node in that system, or if you have a highly structured system where you can automatically know the nodes. But what if you don't? Then it becomes a problem. Another problem it is portability. So we tuned the system for one hardware architecture, then we moved it, and then we need to tune it again. So semi-explicit placement is also about tackling the portability issue. So network scalability. First of all, we group nodes into as groups. And then we have two types of nodes. So it doesn't, by introducing as groups, we don't wipe away the distributed system. So, but as groups is about using, providing programmers additional tool, and that is grouping nodes into some sort of groups. So we have free nodes, and these are actually distributed Erlang nodes, and they can be hidden and they can be normal. And they have just the same properties as they have in distributed Erlang. And then we have as-group nodes. And as-group nodes are the nodes that belong at least to one as-group. So the feature of as-groups is that they are overlapping. So a node can belong to multiple as-groups. And so the thing here is that as nodes in the as groups have transitive connections with the node from the same as groups and non-transitive connections with other nodes. It doesn't matter whether they're from another as group or with free nodes, so non-transitive connections. So this is just an example how it works. So we have two groups of nodes. These are free nodes, and their partitions. So we have 1, 2, 3 connected, and 4, 5, 6 connected. Then, for example, we connect node 3 and 5, and then what we get is a fully connected network. When we have nodes in as groups, they're again transitive connection within those groups, so they just perform just the same as those nodes. But when we connect nodes 3 and 4, they don't share connection, so it just stops there. So what types of connections we have between those nodes? Well, we still have our free nodes, and they behave the same way as in distributed Erlang. So they have fully connected network transitive connections, shared namespace. Then we have those hidden nodes, and the hidden nodes, they don't share connections. So when they establish connection, that is just direct connection, and they don't tell other nodes what other nodes they're connected. And each hidden node, it has its own namespace. What it means, so if even you use global module, for example, to register a name, it will just stay there. It doesn't matter whether it's connected to other free nodes, any nodes. Doesn't matter, they don't share information. And then we have our S-group nodes, and they have transitive connection within nodes, and they have own namespace, but they don't share this information with other nodes. So again. And here the question we very often get, so why S-groups? Well, we considered a number of approaches here. And during these 2 days, we heard other approaches that people use, for example, using hidden nodes and then just establishing those connections, or just switch off this transitive connectivity and just, again, connect nodes to each other. So what we wanted is to preserve Erlang philosophy. And this philosophy is that any node can connect to any other node. So any node can directly be connected to any other. And then we want to reduce, to add and remove nodes to the S-groups really quickly. So by quickly, I mean with no pain, like add, remove, fine. And then we wanted that those nodes could be able to belong to multiple groups. And we wanted this mechanism simple. We didn't want something complicated, really. So we considered grouping nodes using the hash values. But the problem with hash values was that when we started adding nodes into multiple S-groups and removing them, so when we have those dynamic things, so when we add a node to S-group, do we need to change the hash table? What do we need to modify it? How would it work if nodes belong to multiple S-groups? So probably there is a solution there, but we still just didn't see it. Probably somebody later would reduce it. We decided not to go that direction. Then we thought about hierarchical structure. Well, that is quite straightforward, right? So it's something like from DNS, we can think about something like that. Or we can think about like those tree structures when we have a cluster and we have a cloud and have multiple clouds. We can see the tree structure over there. But the problem with this is that it contradicts this philosophy of directly connecting nodes. So if nodes are in hierarchical structure, they just can't connect nodes from different hierarchical level, so we decided not to go there. So what we introduced are our overlapping S-groups. And using overlapping S-groups allows us, first of all, group nodes in partition, like, for example, global groups. So we just, nodes just don't overlap, and then we get this partition. Or we can build nodes in a hierarchical structure, or in any actually structure that we want. So what can we do with those groups? Well, as I said, we can group them into a hierarchical structure. So, for example, we have node A over here, and we want to send a message to node N. So what happens is that, first of all, we partition the whole set of nodes into S-groups. Then we take one node from each group, and we connect them, so creating something like this, so like a hierarchy. And then one node from this one, we connect with one node from that S-group. And what we get is that when we want to send a message from A to N, A sends a message to B, then to D, E, F, N. So messages can be routed like that. But some people can introduce a simple another system. So probably they don't want this strict hierarchical structure. Maybe they want to introduce redundancy in their system. So they can have multiple nodes, for example, here on this top level, multiple gateways, and then multiple nodes here, and they want to communicate with free nodes. So that's also possible if they want that. Or some people may not worry about the number of connections they have, but they're really worried about the namespace they share. So what happens is that we have this largest group, and then in that S group, we just register some names that are used by all nodes. Then we have another group, a bit smaller, that contains nodes from a smaller group of nodes. And finally, we have just tiny, tiny group of nodes that have specific information. Maybe it's often updated or something like that. So we can do that as well. So as group functions, we can add new as group, we can remove as group, add and remove nodes from as groups, and then we can. There are some additional functions. So we can collect information about as groups, about nodes, which as groups it belongs, which names we register, and so on. So all kind of additional functions. So what about scalability? Well, this is, again, the same example I showed you in the beginning when we looked at different types of different percentage of global operations that we have in the system. Well, in the global, using as group, it shows that actually it helps, yeah. The scalability improves. And just to show you how we can structure those groups, how we can use those groups, I'll go through an example. This is an orbit example. So it's a closure symbolic computing kernel. So it's a generalization of transitive closure computation. And what it does actually, so we take a given space from 0 to x, and to this space we apply a set of generators. And these generators, they create a new list. And we continue this process until no new numbers are generated. So this is the example. So for example, we have, all right, so why orbit? Why decided do we use orbit? Well, first of all, it uses a simple structure, for example, like React. So it has this distributed hash table, and which is similar to NoSQL DBMSs. And another thing is that it's peer-to-peer connection. So that's also quite common feature of distributed Erlang applications. And the last thing, well, quite important one, is just a few hundred of lines of code, so we can easily understand it, explain it, and just run the first experiments with it. So we have non-distributed Erlang, we have one node, and we have a master process, and we have worker processes. So what we have is that master process, it generates the first number, and it spawns it. And the worker process, it checks whether this number is already in the table, and if it's in the table, then we just terminate the process, send the results back to the master, and that's it. If the process is not in the table, we put the process in the table, apply the set of generators, we get a new list, and repeat the process from the beginning. So here we have spawn, just a spawn, and we have a set of those modules. And then we want to do distributed Erlang. So now we put our master on a separate node, and workers on the separate node. So the thing here is that the table became a distributed table. So it's not kept on one node anymore, but it's rather distributed hash table on multiple nodes. So when we, the master node, it's again generates the first number, but now it takes the hash value of the number. So, and this hash value defines to which node we need to spawn this process. So we, for example, spawn it to the first node, and then again we check whether the node is already registered, and if it's not registered, we put it in the table, generate the new list of numbers, and the process repeated. So the difference that happened here is that we just modified few modules, that is master and worker node. There were minor modifications, and the main thing that changed that was this spawn link. So instead of sending just to a module, now we send it, we define to which node, particular node, we want to spawn it. And now we moved from distributed Erlang to SD Erlang. So now our distributed hash table is on is over all those nodes. So we again distributed it. But, and master node, it generates the first number, it takes the hash value, but now the hash value defines not the table or the final worker node where our process will be spawned, but it rather defines the subgroup where it will go. So master process generated the number. It spawned, for example, to this as group. Here, when it arrives to this gateway node, we take another hash value. And from this hash value, we define to which exactly node it should go. And as you can see, the transformation is much more complicated now. So what we get, we now need to modify not only one simple, but we need to modify our two modules again. We need to introduce new modules there that will take care of grouping, take care of functionality of the submasters, and Ken team of the release project, they work on the refactoring mechanism. So what we need to introduce there to simplify the process, if we already have a distributed Erlang application and we want to move it from distributed to scalable distributed Erlang. That's the bug. And this is the first measurements that we've got. So we did measurements from 1 to 160 nodes, and that is around 1,300 of cores. And this is throughput, right? Right, and then the number of nodes, so we measure scalability. So the difference, if you notice, well, the difference is not that large. But on another hand, we don't handle that many nodes either. That is 160 nodes, and this is a preliminary results that we show you. But important thing to note here is this change. So actually from up to 20 nodes, distributed Erlang shows better performance, and after that we have this tweak, and scalable distributed Erlang begins to perform better. Another thing to notice here is that we don't use global namespace here. So this particular benchmark, we don't use global names here, like at all. It's fully distributed. So the improvement that we got here is just because of reduced number of connections. Right. So another direction that we work for SD Erlang is semi-explicit placement. So why do we want that? Well, as I said before, we want that for portability reasons. We want because we just we can't expect a programmer to remember thousands of nodes in the network. And another thing is about, well, how we want to put our processes. So whether we want to put them together because they communicate quite a lot. Maybe we want to spawn this process quite far away because we know that the computation is going to take a while. And so we don't want to load our own system, but we better to be it executed in the cloud. Or we want to spawn it nearby because we know it will take just a few minutes, so it's better it be here somewhere. So, and how we tackle that? Well, we notice that those systems that they actually have a tree structure. So something like racks, and then clusters, and then a cloud, for example. And here we use a distant function, like this, where it defines the longest path shared between the root. The shared path from the root between nodes X and Y. So I'll show an example. So for example, nodes B and C, they have 2. The level is 2. And so the distance will be 1/4. But nodes B and G, the shared path is just 1. So the distance will be just half, and so on. So these are measurements that we did at Glasgow University, Harriet-Watt universities, and these are a Beowulf cluster, and these are nodes, and that's another cluster that we have there. So what we did, we measured the distance. So it's actually the main reason we did it is just to prove that actually we can rely on the communication time as some sort of identifier that it really works, that we have close nodes, we have faraway nodes, and we can use those metrics. And for that, we implement a choose node function. So what we have a set of attributes, parameters. This is a list, and we did it like a list because we want to extend it further. For now, we have attributes, and we have as groups. We can use them. So, for example, Node 3 wants to spawn its processes only to the nodes that belong to group 1 and group 2. So it can spawn only node 4. Or we can give attributes to the node. So what sort of attributes do I mean? Well, it's software. So for example, what particular software is available on that particular node. And then, for example, hardware, so on which hardware a node is running, or for example, some properties of the node, right? So whether it's a worker node, it's, I don't know, a server, what sort of node that is. So we can give all sorts of attributes there. And then we can choose a node from just saying, for example, I want this set of attributes, and I want to spawn to any node that has those attributes. And another thing that currently we're working on is about distances. So for example, we want to spawn a process to a node that nearer than 0.04, or something between 0.05 and 0.07, something like that. Another thing that we did was about defining S-group operational semantics. Why do we need that? Well, because we want to reason about our groups. We want to see the properties. We want to see what's happening there. And for that, we need a semantics. And we introduced semantics for 16 functions. 9 of those functions change their state, and 6 of the functions, they just return a value, but don't change actually any state. And this is our semantics. So we have a set of groups, as groups, a set of free groups, a set of free hidden groups, and a set of nodes. And every group is defined by nodes. So all those nodes are defined by nodes, but free hidden group consists of only one node. And every group has a namespace. But as groups, they also have a name. Free hidden groups and free normal groups, they don't have one. And nodes, they have node ID, type, then set of connections and group names that belong to. A nice property that we can see immediately from here is that a node can belong to only one group. Either it's an S-group node, or it's a free normal node, or it's a free hidden node. So if we see that there is some sort of overlapping, then there's definitely something is going wrong over there. So this is how our transition semantics looks like. So we have an initial state. We apply a command on a particular node, and we get a new state, and we get a value. Just to give a flavor what's happening there and how we introduce that, I'll give a simple example with a register name. So we register name on S group in an S group, give it a name, it's a PID, and it's either registered or not registered. So initially we have a set of groups, a set of free groups, a set of free hidden groups, and a set of nodes. We apply register name function, S group name, name PID, or node NI. And then we check whether this particular node belongs to defined group. If it does, then we check whether the name or PID are already registered. If they're not registered, then we register, modify the namespace, and return the new state and the value. Otherwise, just the same state, and we don't register anything. So how we check that it actually works? How do we check that our functions, first of all, that we implemented work, and then the mathematics that we wrote for that are actually true, and the thing that they concur, actually? Well, what we did, we used quick check, fantastic tool. So we have a command, as group command, and now we go into 2 directions. So first, we run the real system. We apply the apply the function in the real system, and we get a new state. And then we do just the same, but for the mathematical part. So we apply our semantics, take abstract model, some abstract state, and we get a new state. And then we check those. So they should concur. If they don't, then something went wrong. This is our precondition, for example, for function new as group. So the precondition here that, well, as group, it can't be empty. There should be at least one node over there. And postcondition is looks like this. So we have abstract state and abstract result. And we apply the function. We take the states, and our abstract state result should be the same as the actual result, and our state should be the same as our abstract state. That's how it works. So our future work. Well, first of all, that's about semi-explicit placement. We think that's really, really nice property that SD Erlang should have, will have, and really work and on that. So first of all, that's about abstract interface. And that is, well, I showed you those numbers, how we calculate how nodes are close or further away from each other. And probably programmers don't want to handle that information, right? It's quite a lot, like knowing, okay, this is on 0.4, that is 0.2. What we may want to have is rather something more straightforward, something like very close or far away, something like real terms over them. And then another thing is that currently what we have is that we have a configuration. So we have this configuration file, and it tells us how far nodes are from each other. And of course, that's not the thing, because we have a dynamic system, and it's go and fall, and they come back, and we want the system to recognize, to see the real system rather than something abstract. And another thing is about reliability. And here is about, again, about falling nodes, and then they come back, first of all, how we discover them, and then how they impact on our structure. Because, for example, if you have a 3-level structure, we add additional nodes. For example, we connect to a cloud, and then we have a 4-level structure. So how we deal with that, we are looking at those problems. Another is running Simjaska. So those of you who attended Simon's talk heard about Simjaska. This is a simulation engine that was developed and maintained by EDF, real-life application that requires a lot of computation. It's a simulation. So we want to run it in a BlueGen, which is approximately 65,000 cores, and we work on first of all running Simjaska on the BlueGen, and then refactoring it using our S groups to check how the performance changed, whether it helped, and how it helped. Well, our ambition is that SD Erlang to become a standard Erlang. We also work on that, and that is about testing just now. So to prove that actually our library that we wrote it's worthwhile, people can use it, and they better use it. So that's what we need to convince OTP team. Another thing is methodology, because refactoring, it's not as straightforward as it was, for example, from non-distributed Erlang to distributed Erlang, because now we need to introduce those gateways, for example, and now for example, even we have something like a master and a slave, for example, nodes, then those submasters, they take functionality from both. So for some applications, that can be quite easy. You can just put submaster in the middle. It acts as a router. We can implement it as a library, and that's fine. But for some application, that can be a problem. So we also work on what is the scalability principle, what advice we can give, what tips, how to refactor problems, systems. And of course, continue to work on the SD Erlang semantics. We found that, writing semantics for a language is really great. First of all, it helped us to look a bit differently at the function that we wrote. It helped us to find problems, something we didn't notice. It made us look at the consistency, so it was really helpful. And then, of course, quick check, using quick check was really, really helpful, because again, we found problems, we found mistakes in the implementation, found mistakes in the mathematics that we did, and some inconsistencies when we used both of them. So it was really, really useful. Right. So these are some sources that some of you may find useful. General information about the release project, then a GitHub repository. So please have a look at SD Erlang. Any feedback will be very much appreciated. Then DE-Bench Orbit. So these are benchmarks that we are working on. Percept2 is the tool we used to refactor and to look how our applications work. Then BenchErl and Simjaska simulation engine, for those of you who are interested in this kind of applications. So thank you, and well, feedback will be very, very much appreciated. Thank you.
Questions? Comments?
No.
Is it possible to change the group, the S group structure? Like the application might want to decide that new nodes should be added to the S group, or
Yes, yes. We implemented a few. So the way you can start a node, I would say, can join as groups two ways. So first of all, that is configuration. So for example, if you expect that your as groups, then the structure is not going to change, you can define that in the beginning, in the configuration, it will read it, it will structure you. And then later, either if you want to modify that configuration, or initially you started without that configuration, you can use dynamic functions, and you can dynamically add nodes, remove nodes, maybe create new S groups if you like. So those functions, they exist, and they're dynamic, and you can do that during the runtime.
and also when you choose a node to run something on, you can specify the attributes. Can these attributes be changed during the runtime of the system?
Well, I suppose so. I mean, for example, if that is something about software, if this is a software attribute, right? So probably it's about modules, available modules that you have on the node, right? So you can load additional modules, and then they become a new attribute. So you also, and for that we also, thank you for the question, I just absolutely forgot to mention that we have dynamic functions for attributes, so you can add attributes, you can remove some attributes, so you can also do that dynamically. We would love to, we are working on that just now, to introduce those attributes that they could be collected from the VM. So that VM would provide those attributes, rather than, because just now what we have is that a programmer himself or herself should like add or remove those attributes, rather than those parameters twiggled during the runtime. Yes, thank you.
So thanks very much again, Natalia, and thanks to everyone who's taken part in the track today.
Yes.
So thanks very much.
Thanks.
So we've got a 5-minute break and then back for 6 o'clock.